again, any function from a natural numbers to R is continuous, and the same is true for any natural number, for a function from any natural numbers to the space M. And then this question that I'm claiming that any reverse function from R into the natural numbers to be continuous must be constant. You know, in fact, I figure it would be easiest to explain this when we talk about connectedness. So I'll just keep it as Y for now, and we will return to this question in a moment. Another idea is this. If I take and I change the domain of the function, so suppose I look at this situation, right? I look at the characteristic function of Q. So you remember what it does. It maps every rational number to 1, and it maps every irrational number to 0. So if I were to define it from Q to R, the function is continuous because it's constant, right? Now, why would constant maps be continuous? Take an open ball in the codomain. The inverse image is either nothing or everything, right? Because either the open ball contains that one constant point, that's the range of the map, or it doesn't. If it doesn't, the preimage is empty set, open, and if it does contain that one point, it's everything. That's in terms of open sets. Geometrically, a constant function is continuous because continuous functions are not supposed to move the points of the space too far apart. If they collapse the space to a singularity, they satisfy this condition naturally. They in fact bring all the points together. So continuous functions, what they roughly do is they attach points. They take a bunch of points and attach them, but they don't rip points apart from one another. So constant map is like taking this piece of paper and crunching it to a point.
What does constant mean?
Constant means in this case it just equals 1. What is it at 1/2? 1/2 is mapped to 1. What is it at 5? 5 is mapped to 1. What is it at any rational number? It's mapped to 1. So it's constant. In other words, it gives you the same output no matter what input you have for this function. So what we're saying is in xq restricted to q simply always gives you the output 1. So it's continuous. If I take the characteristic map from the irrational numbers, this is also continuous. In particular, if I take this map and I restrict it to the irrationals, the constant to which we map is what? 0. So continuous in this case, yet the function, so you see it's continuous on one set, it's continuous on another set, and together they make R, you see? So what we have is relative to this subset, we have continuity. Relative to this subset, we have continuity. Those two subsets make the whole space, yet the function is continuous nowhere. Is continuous nowhere. So they are basically, I'm not necessarily going to pursue the point. The idea is this, right? So you have a complicated map, and you want to express it as a map that basically as a bunch of maps stitched together. So for example, imagine that that my map is basically, this is my carpet, right? This is the carpet. We have one sheet of the carpet and another sheet of the carpet. And let's say I know that that the function I'm dealing with is continuous on this part of the carpet, and is continuous on this part of the carpet. Together, they make out the whole space. So you see, the parts of the carpet in this problem are irrational and rational numbers. Okay? Those are parts of the carpet on which the map is continuous. Now, if it's continuous on one part of the carpet and another, does it imply it's continuous on the whole carpet? This question tells you, this problem tells you, no, it does not. So next you ask, what's the condition for which that would always be true? Right? So you see, so this is not true. Can you come up with a condition or a bunch of conditions that will make this true? Those are called gluing theorems or stitching theorems, because what you do is you look at the action of the map on parts, and then you try to understand what's the action of the map on the whole. So, in general, we are interested in conditions such that, for example, if M can be written as the union of two sets, A union B, like in this case, R is equal to Q union everything but Q, right? M is A union B. F relative to A, in other words, on the space A, just like I did here, restricted to that space, and F restricted to, so I should say then we have a function from M to some space N, and then we have that F restricted to A, and F restricted to B are continuous. What conditions on A and B must we impose to make the whole map continuous? Would suffice to make the map continuous. Okay? So and A and B might not be disjoint, as in this case. They might not be only finitely many of them, it could be infinitely many A and B. So those are gluing lemmas. Gluing, did I spell gluing correctly? Or I'll say stitching. And did I spell this correctly? Stitching conditions. So there is, let's say, there is one lemma, and that tells you that if M is equal to A1, A2, A3, it's the union, I should say. it's A1 union A2 union A sub n. If f restricted to each A sub k is continuous, and if each AK is closed, then f from M to N is continuous. You see where we don't have this assumption satisfied? In this case, neither Q nor R minus Q are closed subsets of R. But if I break the space into finitely many closed sets, could be even overlapping, and I know that the map is continuous when restricted to each of them, the full map must be closed. Now, what I'll leave it to you to verify. Try to prove it. There is another possibility. If I have huge many, maybe not even countably many A's, if they are open, that would work. If M can be equal to the union of A sub alpha for some index alpha, and the A sub alpha are open, and f restricted to A sub alpha is continuous, then f from M to N is continuous. Okay? So I'm not going to prove it here. I'm not going to deal too much with it in this class, but that becomes important. That might become important as you study more sophisticated analysis problems. Yeah, so you see, notice it's not a coincidence that we only have finitely many closed sets, and it's not a coincidence that here we take the union to be anything as long as those sets are open. Okay? Yes.
Can you construct a piecewise function from n to r such that, like, if you take a f of anything in not equal to 0 is 10, and f of 0 is 0, right? Then 10 minus 0 is bigger than any epsilon you can think of below 10, right?
Your function is over n, over the natural numbers. So did I hear correctly? 10 is mapped to 0. Everything else is mapped somewhere else.
Everything is mapped to 10 except f of 0 is 0.
Okay, so at 0 and 0, everything else is constant. Okay.
So 10 minus 0 is 10, which is bigger than epsilon. If you say epsilon is 1, epsilon is 2, it's bigger than all those epsilons. So why is that continuous?
Because, well, first of all, you make the mistake of watching this function over R. You don't have your spaces. You see, the space that you are looking at is like this. So it's let's say a bunch of points, and then here is a point, and here is a bunch of points. You make the mistake of thinking that those points are inside of R. You're implicitly thinking of this function as in R, in which case it's not continuous. But basically there is nothing between one point and another. There is just nothing at all. You are basically, what is happening is you're thinking of actually a function from some sort of version of a function in R. Let's see, what else? So here is another example that we can consider of continuous functions on abstract spaces. So let MD be a metric space. Let Y belonging to M be some point. Then we can construct a function of this form, f from the metric space MD into R, defined as follows. So you take f of x for any x, will be simply the distance between this x and y. You understand? So for any point, so I took a point y, and now I pick any point x in that metric space, and f of x is going to be the distance. So at which value is 0 attained? F of what value gives you 0? Y. Is there other points at which you get 0? No. So there is only one preimage of 0, right? The inverse image of 0, 0 is in this codomain, is y. Again, another very trivial question. Is this not f that I defined? Is it surjective? Is it onto? Do I construct this way all real numbers or not all real numbers? Which real numbers I cannot construct? And basically this is just a very basic comprehension questions. Which values is this function not able to produce? It's a distance function, so which value cannot not produce? What? Negative numbers, thank you. This function is continuous. How do I know? Well, we can use, not only is it continuous, it has this interesting property. Let's see. What will be if I take the distance between some f of x and f of z? I really used y, so, right? So just take a distance between 2 points, and I want to say, well, if x and z are close, will it imply that f of x and f of z are close? And we have this inequality. So this is simply the distance from x to y minus the distance from x to z. Absolute value, I think you solved this problem. What will that be? That will be less than or equal to the distance between x and z. Agreed? Why is that so? Just look at the triangle inequality. Let me remind you from exam 1. So what can we do? I can take distance from x to y. This is less than or equal to the distance from x to z plus the distance of y to z. Agreed? That's triangle inequality. So if I subtract, I see that distance from x to y minus the distance from x to z is less than or equal to the distance of
You have to do it a different way. You have to start from the distance from x to z.
That's right, thank you. It works, but then it's just, I have to switch the letters. So if I start distance from x to z, that would be the distance from x to y plus the distance from y to z. Right? So that would be what? So I have that.
Just move the distance of y to z to the other side.
Yeah, I mean, what I'm saying, if this is right, it's just I'm getting, I'm getting the variables switched. So less than distance x, y. It's just I used here z instead of y, right? That's what I'm saying. So what you corrected me will end up switching the variables. But you have this, and similarly you will have that distance. So let me just. So just this triangle inequality that we have the distance of, I don't know, I'm glitching. I'm not, I'm just going to say, well, you know how to do it. In other words, what I was doing, it would work, but when I just was writing, I don't remember the first or the second thing. I think it will switch the y and the z. It would make this the absolute value of distance from x to y to x. It will basically switch the roles of y and z. What I was writing, right? And I'm just right now glitching with it, right? So you know how to do it. So
The reason you're messing up is you have
there isn't what I was writing. I think after when you corrected me, I would get that distance of from x to y will be bigger than the distance between xz and yz.
the first statement is wrong. That's why distance from x to y minus the distance from x to z is not less than the distance of x to z.
Right. So this what I wrote here, something is wrong, right?
That's why you were.
So the distance. Distance from x to that's distance x to y minus the distance of x to z would be less than the distance of x to z to y. Yes. The z to y. Yeah, and that would be distance less than or equal to distance from x to z. Thank you. Yes, good that you see. Ta-da. All right, so there is a similar idea we can take given some subset A which belongs to the metric space MD, I can define a function f from M to R, and this time I define the distance of I define f of x to be the distance between x and the set A. So what is that? This is simply the infimum of the distances between x and y, where the infimum is taken over all y in the space A. And you can similarly verify that the absolute value of the distance, so basically if I take absolute value of f of x minus f of z, what will I get? That simply is the distance x to a minus distance z to a, and just like with this inequality, you just have to use infimums, that will be less than or equal to simply the distance between x and z. Okay? So make sure that you see this. So this map in particular is very continuous. I can take delta of epsilon to equal epsilon. So those functions, the last function that I wrote on the board, this is question. So given the space M D, given a space MD, and some set E, which is a subset of M, under what conditions could we conclude that E equals to the inverse image of 0 for some continuous map f from E into R. Okay? So in other words, well, suppose I picked a set E. Could it be the kernel or the set that is mapped to 0 of some continuous map? Okay? And the answer, very simply, if f is continuous, so f is so not E, this should be f from M. Right? So if f is continuous, then E equal to f inverse of 0 must be what? This is a preimage of 0. What must it be?
Close.
No, not necessarily constant. There are plenty of maps that, so I might map, that depends what M is. Let's say if I take M to be R, I might make it the identity, for example, right? There is an identity map. I don't know anything about M. It could be that all the points are mapped to 0, right? That would work, right? I can make M the kernel. All the points are mapped to 0. So it could equal to M. So what I know about the set E, it must be a what? 0 is a singleton. Singletons in R are closed. Therefore, the inverse image of a closed set is closed. So E must be closed. Again, I write twice, so you will think about it. Okay? So in other words, the only sets that could be the kernels of continuous map have to be closed sets. Now, given any closed set E, which is a subset of M, consider the inverse image. Consider, first of all, a function f sub E defined from M to R, where Fe of x is simply the distance of x to the set E. This is a closed set. The only way this function is 0 is that the distance to the set is 0. You understand what I'm saying? So here is E. And what is this function going to do? If you're giving me x here, it will measure the distance to that set. In other words, it will try to find the closest path to the set E. It seems that the closest path, or maybe it's here. So that's the length of this red line. That would be the distance x to E. Okay? So when is this function 0? If x is outside of E, could it possibly be 0? You can see that the distance is positive, so it cannot be 0 if x is outside of E. If x is inside of E, it will be 0. And notice that if x is arbitrarily close to E, it must be part of E because the set is closed. Okay? So what I'm saying, again, hopefully you understood it. So this map equals 0 if and only if x is an element of E. It's not true with not closed sets, you see? So the other possibility is that this boundary is not part of E and you are on the boundary. The distance of the boundary to the set is always 0. But the closed set contains its boundary. So what this is saying is that the inverse image of 0 is your set E. The only things that are mapped to 0 are points in E. Let me give you a quick comprehension check. All you have to do is decide if the sets are closed, open, neither. So here is one example, okay? So I have the set A, which is x squared less than 2y, where the points are x, y in R2. So I'll take this A as a subset of R2. Is A open, closed, neither? Look at the set. It's the set of points where the square of the first coordinate is less than twice the second coordinate. So let me help you, right? If it takes you longer than a second, means you're not doing it right. So this set right away is open. Why is it open? Well, I can do the following. This is the same. So A might also be written as the set x squared minus 2y less than 0. I wrote it, so I wrote it kind of in a weird way. Yes, I should have written here. I should have written the set of all x, y in R2 with the property that x squared is less than 2y. Sorry, that makes better sense. Okay, so A is essentially the set of all x, y such that x squared minus 2y is less than 0. You see this? So what I can do is I can define that the map f from R2 to R2, from R2 to R, my apologies, be f of xy equal to x squared minus 2y. This is clearly continuous. If you remember Calc 3 or anything like that, this is very easily continuous. You can take sequential approach. Take any sequence xn, yn that converges somewhere, that implies xn converges to x, yn converges to y, and that will clearly force this to converge. So you can see that it's continuous by sequential approach, right? So this is the function. Then f is continuous. And what is A in terms of f? A is the inverse image of what? So I'm claiming it's an open set because I'm claiming it's an inverse image of some open set. What's that set? The function maps into R. What's the set?
Negative numbers?
Exactly. So the inverse image of the open interval minus infinity to 0, and that's an open set. So this guy is open, which implies that this guy must be open. There are plenty of other ways of, without doing this process, to know that this is an open set. You can go directly verify it's an open set, but if you understand certain continuous functions, you can just use that. You see? So let's try B. So what about the set B, which equals to xy in R2 such that cosine of xy is bigger than or equal to minus 5y less than or equal to well, I won't use cosine. I don't know how comfortable you are. It's all not a big problem, but let's say I'll say x cubed. X cubed is x cubed times y squared is bigger or equal to minus 5y less than or equal to 7y. Okay, I'm just throwing things out. It could have been cosine, I just don't know. So open, closed, neither. How would I know?
Closed.
Yeah, it is closed. Now, one way to see that this is closed, so let's have two functions, f from R to R, and this function is fxy equals to x cubed y squared plus 5y. That's one of them. And another function is, well, we have g. So g xy will equal to x cubed y squared minus 7y. Okay? Then notice, right? So what must be, so this inequality, it must be less than or equal to 0. I'll write to myself that this guy is less than or equal to 0. And this guy has to be bigger than or equal to 0. Yes? You see, with R, you can always move things so that it's always about 0 if you want to. Okay? So then, what can I see? So those functions, do you agree they are continuous? Both f and g are continuous. Hence what? So hence the set that I want, the set B, is what? It's, I need to take the inverse image under f of what value? Of what? F B is f inverse, this is bigger than 0. Of what? Of the set 0 to infinity. That will satisfy this inequality. Okay? But that's not enough to satisfy this inequality. This g must be less than or equal to 0. So that would be intersection g inverse of what? Yeah, so that would be from minus infinity to 0 included. Okay? Now both sets are closed. You see, this set is closed, so this is closed. This is closed, so this is closed. Intersection of two closed sets is closed. So this guy is closed. And this guy is closed. Therefore, B is closed. You understand the idea? So you can always operate, so as long as you can recognize continuous functions, especially when it's in your familiar spaces, you can use this strategy to find closed sets. Continuous functions tell you a lot about open and closed sets. In fact, if you know all the possibilities for continuous functions, you should know, theoretically, all the possibilities of the open and closed sets of the domain. If you know all the closed and open sets, you should know everything about what the continuous functions look like. Good? So somewhere on the second exam, you have problems like this. There is a very nice way of solving it, and that would be what I just showed you. Good? All right, we have only a few minutes, but perhaps we'll start one of the important topics. So what I feel terribly about the semester is I don't think we're really connected. We only have, what, maybe 2 lessons left to do it. Connectedness. What does it mean to be connected?
That was a joke.
Connectedness. The most hostile class I've ever had, honestly. Such frowning faces. Oh, I guess I got old. So, this, by the way, the full video is already available and you should watch it. I talked about it in previous classes. Watch it so that you know compactness, connectedness before the semester is done. But let's try to understand what is it that we mean when the object is one whole, one piece. Okay? So my explanation is, well, this is what I illustrate, right? So I think, let's take an urn that you find in archaeology. So this is an urn. So this urn is connected, right? It's one piece. I haven't explained what one piece means, but we would say that this urn is connected. Okay? So you go into a museum, you see this wonderful urn, it's one piece, it's connected. Then in the next exhibit, right in front of it, you see another urn, and it was a bit fragile. So what you see is you see cracks. Okay? And on those cracks you see two parts that kind of look like they have no cracks, and they are one piece. So you would say this is A, and this is piece B. But there is glue between the cracks, so if you pick this urn, it's one piece. It's connected. And then you go to the next exhibit, and what you see is this situation. Again, you have some piece, and then it could be more pieces, right? You just can arbitrarily group some pieces in A and other pieces in B. Now, this you would claim is not connected, yes? Now, what's the difference? Okay, what am I trying to illustrate here? Let's see, what is this A and B? We know that, so this urn is your urn M. The full space is the urn M. So this is also M, and this is also M. Right? Different M's, whatever, right? So there is not much to say about this part. What am I really saying here? So what's the relationship between A and B as sets?
We stitch together two continuous sets.
Well, sets cannot be continuous. Continuity is a property of a function. So I stitch something together, but what did I stitch together? What's the relationship between A and B? So what A and B make up together?
Well, they complement each other.
Wonderful. They complement each other. So what I have is, this is connected. This is saying that, well, I found one piece A, and I found another piece B. And I found another piece B. And what do I know about A and B? I know that if I bring them together, I get my full urn, my full space. So that's M. And what else do I know about A and B? I know that if I take A and I take the intersection of A with B, it's empty, yes? A intersection with B, that's what we just heard, is that they complement each other. A intersection B is the empty set. I'm just trying to capture this notion of what I mean an object to be one whole piece. So the crack that I did here is I separated the urn into disjoint pieces. I could have made more cracks here, but I could just gather them into two parts, right? So A and B, and let's say A and B are disjoint parts of the urn. And yet in this situation they are connected, whereas we have the same situation in here, right? No, not quite the same. Let's see what's the difference. This is A, this is B. The union of A and B gives you the full urn, just like before, and yet not connected. So again, this is A, and then we have B. Why is this not connected? How would you try to explain the difference? Any ideas? What's the difference between this situation and that situation? Any ideas? Yes? Julio?
A might not necessarily be the complement of B.
In both cases they are. That's what we're saying. A union B is M, A intersection B is empty. They must be complements of one another. No? Right? So what else? Yes, there in the back?
Because you can say that there is an open set in between A and B.
Okay, but okay, wonderful. What does the open set mean? What's true about A and B? Why in this case we don't say they are connected? Any ideas? What is that open set? You might have seen the definition, you might have understood it just on the spot. What are you trying to say?
Something to do with the distance.
Something to do with the distance. Those two objects are separate. So what I can do is, if I'm an archaeologist, I can wrap A in bubble wrap that is separate from the bubble wrap of the other part, right? So what I can do is I can go and carefully wrap this up, and let's call this wrap U, and let's try to take another wrap here and call this other wrap V. V. Now open sets means that each point here has a protective distance. In other words, no point on the boundary of A is in contact with boundary B. That's what open provides us, okay? It protects. You see, open sets, they protect. So this part A is protected from banging against B. It's a bubble wrap. That's where I again mentioned that open sets have this analogy of they protect things, they make things safe. So what you have here is, we have the following definition that I try to suggest here, is that definition, this is definition of disconnectedness. We would say that M is disconnected or not connected if M equals U union V, where U, V are open sets. So you can see they're open sets. Why open? The idea of open is that there's air. So there is a distance, as you mentioned, right? Open sets. And open sets in M, open sets in M, and U intersect V is what? Empty. So this set is called disconnection. So the collection U, V is called the disconnection, or a disconnection. Of M. A set is connected if disconnection is not possible. So let's say here, no matter how you try, you cannot separate it into two pieces that don't touch. So you would say definition, M is connected if it is not disconnected. In other words, if it's impossible to do this. I think we're out of time. Now, over the break, make sure to watch the video on connectedness so that all of this is old stuff.